Hello everyone, and welcome back to another video where we are going to be speedrunning complex analysing a Maths 505 integral. So let's get started, shall we? The first thing we're going to do is express this cosine of sine term in terms of e. And then we're going to express the whole numerator in terms of the exponential. So one thing we can actually note is that cosine of sine of x is actually just going to be equal to the real part of e to the I sine of x right here. Because by Euler's formula, the real part of that is just going to be cosine of sine of x, and then the imaginary part would be I sine of x. I'm not stuttering, this is the actual function. So substituting this in, we find that our integral is just the integral over all real numbers of e to the cosine of x, and then by properties of exponents, we have plus I sine of x, and then the real part, of course, I'll write that up front, divided by x squared plus 1 dx. But we also know by Euler's formula again that right there is just e to the xi. So our actual integral right here takes the form of the following: the real part of the integral over all real numbers of e to the xi divided by x squared plus 1 dx. And because the exponential and complex exponential are analytic over the entire complex plane, we know that our only poles are going to be from this thing right here at I and negative I. But note that this is an integral over all real numbers, meaning that the contour we're going to be using, or that we want to use, is the upper semicircular one right here. So we're integrating this way with our one little pole at I. By Jordan's lemma, we're going to say that this outer ring right here goes to 0, so I'll actually write this out. The line integral is going to be equal to the integral over gamma 1, right? Gamma 1, and you have gamma 2, plus the integral over gamma 2. But this integral over gamma 2 is going to be 0 by Jordan's lemma, and this right here is going to be equal to I right here, our integral. So what we're going to do then is just, by the residue theorem, say that this is equal to 2 pi I times the residue at I. And now it's just a question of calculating 2 pi I, or really the residue, at I of this function right here. And let's do that real fast, shall we? What we have is e to the xi divided by x squared plus 1. And then we're going to have x minus I right here. And the limit as x approaches I. And we'll note that these terms cancel because this can be factored as x plus I, x minus I, and we'll see this cancel right there, meaning that we can just plug and chug. In the denominator we have 2i, and in the numerator we have e to the I squared, which is just negative 1, which is e to the negative 1, which is just 1 over e. So, since this is our residue, we just have to multiply by 2 pi I, and the 2 i's cancel, meaning we're just left with pi e to the 1 over e. And that right there is our answer. I hope you all enjoyed this video, rather quick one, and I'll see you in the next one. Thank you for watching.